Oh, hello. Wow, okay. So, today we're going to finally actually do a proof. We spent the last, I think, couple of streams. We did have some interesting theorems, but mostly spent the last couple of streams attempting to come up with some version of inverse function theorem that would generalize nicely. Weren't able to do that. So instead we're going to do what I had done in my original draft. I think I will hide these theorems for now, and we might put them somewhere else. I'm not sure. These ones are all very nice. These ones and this one and this one. We'll figure out where to put these. But right now I'm just going to comment them out of the paper. Okay, let's see. Okay, I'll figure out where to put these theorems later. But for now, we're just going to actually prove the theorem we want to prove. Okay, so all of this is not useful, unfortunately. This is very unfortunate. Maybe I will prove these in another theorem somewhere else. Just that we can have this explicit expression. But for now, all of this is going away. Okay, so our theorem is still we have let f be analytic at x0 with f prime as a unit. Then f has an analytic local inverse function near x0. Okay, so we're going to take a simple case first. So we'll say take the special case that f is given by a convergent power series. Say f of x equals summation cos n of coefficients alpha n times x prime. Actually, we'll say special case of that. We'll say x0 equals 0 and f of x0 equals 0, and all of this is not necessary, but this is fine. And f prime at x0 is 1. So the reason this special case will work, so we'll say if we can find a if we can prove, or rather, if we can find an inverse function, a local inverse function for f in this case, then for any g, any analytic, we can let f of x equal to g of x plus x0 divided by g prime at x0. Then the inverse function, f inverse, sorry, hold on, let me think about that. Okay, so we take the special case that x0 is 0, f of x0 is also 0, and f prime at x0 is 1. If we can find a local inverse, if we can, prove the theorem in this limited case, then for analytic g, we can let, so f of x will be this, and then we'll also do g of x plus x0 minus g at x0, and then divided by g prime at x0. And then g inverse at y is given by, I think, place x with f inverse of, let me think, hold on. So actually we just want to solve this for g inverse. So if f of x is this, then we can say if y is g of, let's say, inverse function f inverse of all of this mess will be x. And then replace x with x minus x0. And then add x0. And so if x is g inverse of y, and then this will be y. Okay, so our special case is x0 is 0, f of x0 is 0, and f prime x0 is 1. If you can prove the theorem in this case, then for analytic g, we can let f of x be this, which satisfies criteria, and then this will hold. Yes. So G inverse at y will be centered around y near G of x0. Okay, yeah. Yeah, so this is our special case. So we take the special case where x0 is 0 and f of x0 is 0 and f prime is x0, x0 is 1. And then we'll say we also take the case where f of x equals the sum, we already have this written out, and S, the domain, is just a set of x in A such that P1 of x is strictly less than phi alpha. So the first special case is we take, we just sort of do some linear transformations to make it a little easier on ourselves. So the center is 0, and the center of the output is also 0, and the slope is 1. And then we say, we're also going to take the case where f is this power series, and we have this expression, and then we can say, if we can find a inverse function for f, in this case, then the general case is obtained by restricting the domain. Right, so instead of assuming we have a really complicated domain, so here we're not making any restrictions on the domain S in this general case. We're saying we're just going to take this special case where the domain is this full cylinder set. So it's the entire sort of the maximum open set on which our power series converges. So we're going to take this whole set here. Okay, so now, so what we want to do is actually one more thing to sort of simplify this. So we'll say lastly, actually, well, okay, let's do this. Okay, so since f prime at 0 is in A star. Actually, let me think on this one second. Okay, we'll do it this way. So notice that the set S is, oh, we are going to need to prove that it's locally injective, I think. Okay. Let's actually do that. So we do have to prove that it's locally injective. That's necessary. These are not used, though. These are not used for that. I think our theorem, the theorem that we want to reference, is we placed it in the differentiability section. See if I can find it. This is power series, I think. No, this is integration. And this is differentiation. Okay, so differentiable for each index. The projection is differentiable, blah, blah, blah. Maybe it's down at the end of integration, actually. Okay. Well, yes, it is. Okay, so let f be continuously differentiable on a locally convex set. Then f prime can be given by this limit. And the corollary to that is let S be locally convex and f be continuously differentiable. Then there is a neighborhood of x0 over which f is injective. Okay. So the set S is open and locally convex. Actually, we'll just say, let's label this theorem. Okay, so we were right here. There we are. So S is locally convex, and since and f prime at 0 is non-zero, so by this theorem, continuously differentiable function f is locally injective. So we'll say it follows that there is a relatively open set U subset to S over which f is injective. So there must be an inverse function for over the image. So I'll say G f inverse, which maps the image f of u to u. So the first thing we're noting is that we have an inverse function because our function is locally injective. We have a neighborhood over which it's injective, and then a function which is injective on a set is bijective to its image. So, so we have this inverse function, and then we'll say first we prove that f inverse is continuous. And then let me check my notes here, because this is the hard part. So, we'll prove that f inverse is continuous. So we're going to invoke the inverse function theorem for complex functions. But first, so we'll say, okay, let y be in f of u. Actually, we'll just say that f inverse is continuous. In doing this, we will prove the stronger result that the image f of u is an open set. We'll say let y be in actually we'll just say y sub n be subset to y sub n be subset to a be any sequence having y sub n go to 0. So y sub n is going in is a sequence tending to 0. We're going to prove we shall prove that for all sufficiently large n, that y sub n is in f of u, and also f inverse, or sorry, this should be, yeah, f inverse of y sub n goes to 0. This doesn't jive with what we set up. This will still work, but this doesn't agree with what we set up. If we want to prove that, if we want to prove the general case where we have a power series, it actually doesn't make sense with this. That's fine though. Let's adjust this slightly. We'll say we also take the case where the domain S is an open set. We'll do it that way. The general case is obtained by restricting the domain. Let's be also a little more explicit in this theorem about what we're trying to say. So f map S to A be analytic, then there is a neighborhood x0 in U subset to S over which and a analytic function f inverse, which maps the image f of u to over which f inverse of f of x equals f of f inverse of x, which is x. Actually, we'll say this should be y. F inverse of y. Yes, that's correct. Okay, let's be specific here. We should have 0 in U. So from this theorem, we have f being locally injective, so we have this relatively open set with 0 in it. Must be an inverse function defined on the image. F inverse mapping U, f of U to U. We first prove that f inverse is continuous. Actually, we can probably make another note here. We can say I think what we want to do is we can just show that f is continuous, f inverse is continuous at 0. I think if we do that, we can also, that will also generalize. maybe. We might have to do it all out. It's not going to matter much in the end. I just want to try to keep it simpler. So I think we are going to end up having x zeros and such. But that's fine. Doing the translation means it's a little simpler. Okay. Okay, so we'll say, actually we're gonna add a note. We're going to say, without loss of generality, we may also assume that f prime of u is subset to a star. Oops. This is valid since A star is an open set and f prime is continuous with f prime at 0 being 1, which is an A star. So because f is continuous, and, oh gosh, because f is continuous and f prime at 0 is a unit, and the set of units is an open set, then we're just going to make our neighborhood of 0, so we've taken this neighborhood. So we're just going to restrict this neighborhood such that f prime is always a unit in this neighborhood. So just make this neighborhood small enough that it's always a unit, which is valid since f prime at 0 is a unit. Okay. So first we'll prove that f inverse is continuous. So we'll say let y sub n, actually we'll say let x0 be in the, let me think on this. Let y0 be in the image f of u, and let y sub n be a sequence having y sub n goes to y0. We shall prove that for all sufficiently large n, that y sub n is an f of u, and also f inverse of y sub n goes to f inverse of y0. So that's our goal. So we're going to have the sequence of y's, and we're going to prove that that for any sequence of y's approaching y0, that eventually it'll be an f of u. So this will prove that f of u is an open set, and it will also we'll also have that this f inverse of y sub n tends to f inverse of y0. So we'll have both of those conditions being proven. Okay, so in order to do this, so we're going to prove that eventually y sub n is an f of u, and also this limit condition is satisfied. So we're going to work on the first part first. We're going to show that eventually y sub n is in this image, and we will do that by explicitly constructing the inverse. So we're going to have to invoke inverse function theorem first for complex analytic functions. Okay, so we'll say since let me think on this. Actually, we're going to maybe need a little more. So the goal here is to essentially only use the power series. Okay, we're just gonna start right away. Okay, so we're gonna say let f, actually we'll do this. Let f of x be defined as the summation on n, and then we have f nth derivative at 0 divided by n factorial times x power n. So f is defined as this, and we will take the domain okay. Okay, we'll do this. Okay. Let C be the set of x in A such that we have P1 of x is less than, actually we'll do it this way also. Okay, let alpha sub n be equal to these fractions. And notice that alpha 0 is f of 0 and alpha 1 is f prime at 1. Then we'll say consider the function capital F of x is defined as the summation, and we have alpha sub n x power n. Actually, we can probably do, this is fine. C be the set such that P1 of x is less than phi of alpha, and also f prime of x, we can say f prime at P1 of x is less than, oh sorry, non-zero, I think. Let me see how that looks. So we're gonna have alpha and are these terms, and we're just noticing that alpha 0 is 0, alpha 1 is 1. So alpha 0 is f at 0. Alpha 1 is the slope, which is 1. Or sorry, this should be f prime at 0. And we're going to consider the function, this f of x, which is defined as the summation, and let C be this set. So this set is the set over which x and A has, so P1 of x is less than phi alpha, so that means this should be 1 over phi alpha, actually. Should be, let me fix that. So f of x is, P1 of f of x is less than 1 over phi alpha, so the power series converges. And also, f prime at p1 of x is non-zero. Actually, we can say f prime at p1 of x is in a star, because that's actually what we want. Okay, so we'll do that. So C is a cylinder set. So we'll say by analyticity of F, we do have f of x equals f of x for all x. Actually, we can say for all x in some S neighborhood of 0. Okay, so this is sort of what we want to do. Okay, so we're going to say this set C is locally convex, and this capital F function is continuously differentiable. We could probably call this G or something, I don't know. But C is locally convex and open. And F is continuously, capital F is continuously differentiable, and F prime at 0 is not equal to 0. So by this locally injective theorem, we have capital F being locally injective. Whoopsies. This, okay. Let's maybe also be even more explicit about what we're doing. So our proof strategy is to prove that our function is an open mapping. So we'll say alpha n be this, and notice that alpha 0 is f0, 0, this is this. Consider this function. By analyticity, we do have f of x equals f of x for all x in some S neighborhood of 0. Since C is locally convex and open, F is continuously differentiable, and f prime of 0 is non-zero. So by this, we have F being locally injective. So there's a relatively open set. So there is a relatively open set containing 0, so some set U containing 0, and actually instead of S, this should be, we're moving over to C. Actually, okay. Let's do this even more explicitly. Okay, we'll just do it this way. So we're gonna say, be really super explicit. In order to prove the theorem, we're going to prove that power series are open maps. So we'll say, we'll say power series are open maps when their derivative is always a unit. So we'll say, let alpha be in a and 0, and let f and we'll say f of x be equal to, and I'll do capital F. F of x be the summation n alpha sub n times x power n. Then we'll say, to prove that f, actually we'll say this and let this, okay. And then we'll say, to prove that consider, oh gosh. Okay, so we'll say, take the restriction that mostly just this wording is really tripping me up for how to word this. If alpha 1 is and J star. Actually, we can just say equals 1. No, I'll take A star. No, I will do 1. Okay, so we shall prove that for any neighborhood, or rather, oh gosh, this is really weird. Given any sequence y sub n indexed by n in naturals, having okay, so given any sequence yn having y sub n go to 0, there is a sequence, so we'll just do x sub n having x sub n go to 0 with f of x0 equals y0, or sorry, xn. For all n. I made a typo somewhere. But where? Oh, there it is. Okay, so we're gonna prove Okay. We'll do it like this. Okay. So the alpha be some coefficients, and take the case that alpha 0 is 0 and alpha 1 is 1, and let capital F of x be the summation, this power series. We shall prove that given any sequence y tending to 0, there is also a sequence xn tending to 0 with f of xn is yn for all n. Or we can say for all sufficiently large n. Okay. Okay, we'll do this. Okay, so first we have to construct our sequence of xn. So the first step we have to do is essentially we're going to construct this on each projection. So we'll say okay, so we'll say consider the function f sub 1 of x defined as equaling the summation across n of p1 of alpha times x to the n. And we'll say, notice that if we restrict x in C, then f sub 1 is complex analytic, and moreover, actually we can just say, notice that f is complex analytic. So by inverse function theorem from complex analysis, actually we say f is complex analytic with f1 prime at 0 equals 1. So by inverse function for complex analysis, there is an inverse function f sub 1 inverse. Actually we can say it is possible to find f1 of x defined as the summation, f is complex analytic with f1 prime 0 is 0. Do I need this? Yes, I need this. Okay. This should be f sub 1. It's complex analytic with f1 prime at 0 is 1. So when restricting x and c by the inverse function theorem, actually we can say since we have p1 of y sub n going to 0, so p1 of yn is going to 0 with p1 of y sub n in C, then, okay, by inverse function theorem from complex analysis, we can find a sequence of, and we'll call these x sub 1, comma n, actually, no, x sub n, comma 1. In C, having x and 1 going to 0 with capital F1 each x sub n 1 equaling y sub n, p1 of y sub n. Okay, yes, so we're going to consider this function f1. So we have this sequence of y sub n's. They're tending to 0. Since y sub n's are tending to 0, then the projection p1 of y sub n is also tending to 0. So we're going to consider this function f sub 1, which is just, it's the same power series, but we're using p1 of alpha. So we'll say, notice that f1 is complex analytic near 0, with f1 prime at 0 is 1, and f1 at 0 is also 0. Okay. Okay, and then we can say, since we have these p1 of y sub n going to 0 as complex numbers, then by the inverse function theorem from complex analysis, we find this sequence x sub n 1 in C having x sub n 1 go to 0, with all f1 of x n 1 equal p1 y sub n. Okay. Now we will say, so here's going to be our general construction. We'll say for every m in natural, actually let me say every integer m greater than 1, define x sub nm inductively as follows. Okay, so we have our inductive definition is w sub n comma m is equal to we have p1 of f prime at w sub n1, and this is in the top we have y sub n pm of y sub n minus capital F of x n m minus 1. I think that's correct. This should be, sorry, this should be e sub m times that, and we're also adding w sub n comma m minus 1. Sorry, not w, these are x's. Okay, Okay, we want to specify, so here's 0 with f1 0, so there's this. Okay, so we can say this is valid. Sorry, this construction is valid since for all sufficiently large n, we should have f prime at x sub n1 is in A star. Sorry, my subscript didn't work. Okay. Oh, I guess these assumptions ended up not being important at all, didn't they? I think none of these are important. Are they? Let me double check. Yeah, that's fine. Okay. Okay, since we have p1y is then going to 0, p1y is then in C. Okay, so for all sufficiently large n, we should have, we should say valid for all sufficiently large n, since eventually, actually we can say since p1 of f prime at x sub n minus n1 is f1 prime at x n1 is eventually non-zero. Okay, and then we can say okay, so this is our thing. So what we want to have is okay, so we'll say, notice that for all k less than m, we have p sub k at w sub nm equaling p sub k, actually we can just say, yeah, p sub k of w sub nk which is this fraction, but without e sub m, and in the case m equals k. So in particular, for each n, we have a convergent limit x n m goes to x span. Okay. I actually don't need this part. This is just clutter. Okay. We shall prove that f of x sub n equals f actually just equals y sub n. Okay. So our goal is we're going to have this powered series, and we're going to prove that this sequence has this sequence x sub n, which tends to 0. And we're going to say we want to prove that x sub n converges to 0, and we also want to prove that f at x sub n is equal to y sub n. Okay, so to prove x sub n, capital F of x sub n equals y sub n, we'll say Okay, so we'll say to prove f x n equals y sub n, let k in, actually we'll say suppose that is the z of f at x sub n minus y sub n equals k, or sorry, is greater than or equal to k. Okay, so take some k in natural and suppose that this is greater than or equal to k, which is vacuously true, or rather trivially true when k equals 1. If we do have, actually we'll do it by induction. Okay, so we're going to prove by induction that this z value is greater than or equal to any k for each k in naturals. So in the case for k equals 1, we're going to use our premise. So we have f, capital F, we'll do p1, f at x sub n. This is equal to sum n in n0 would just be explicit, n equals 0 to infinity, and we have p sub 1 alpha n times x power n, yes, which is p1 alpha n, p1 x, this should be, oh gosh, we have too many indices. Oh, let's do a j. J to infinity, alpha j, instead of x power j, it should be x sub n power j. Okay, and then we have this one, this should still be j, this one's j, this one's j, this should be x sub n, and p1 of x sub n is just x sub n comma 1, but now this is just f sub 1 at x sub n1, and we know that by premise this is y sub n, or sorry, p1 of y sub n. Okay, so we're saying so we're going to set this, so we do the setup, we say f1 is the same sequence, the same power series as f, but we're just using p1 of alpha. Since f1 is complex analytic by inverse function theorem, we find, since f1 is complex analytic near 0, with f1 prime of 0 is p1 of alpha 1, which is non-zero, since alpha 1 is a unit. Then since we have p1 of y sub n going to 0, so p1 are complex numbers tending to 0, by inverse function theorem from complex analysis, we also find this xn1 tending to 0 with all of these. We define these xn's inductively, and we note that they have a limit with m. For each fixed n, they have a limit with m going to infinity. And we know that they have a limit since, in terms of m, since for every k less than m, we just have p sub k, these should be x's again. P sub k of x and m is just P sub k of x and k. So each time we're just including, we're just doing this E sub m times this thing. We're just taking the previous one and adding something on the mth index. And this is on the mth index since these we're doing these projections, Pm and P1. So this is some complex number. So we're just adding some complex number on the mth index for each m. So if k is less than m, then the kth projection on m is the same as the kth projection on x on the k. In particular, this holds for 1. So we get from this we get this convergent limit since each one is eventually since each projection is eventually constant as m increases, then we do have this limit. For each fixed n, we have this limit as m goes to infinity. So then we're going to prove this. So we're going to assume, suppose z of f xn minus yn is greater than or equal to k. So for the case k equals 1, so p1 of f at xn, so we just do, this is the sum of the p1s of alpha j, xn j. And this is, because p1 is a multiplicative function, this is p1 alpha j, p1 xn power j, but p1 of xn, this is just xn1, or p1 of xn1, but xn1 are complex numbers, so it's just xn1 power j, but this is f sub 1 at xn1, and xn1 were specifically selected so that this is p1 of y sub n, so this is p1 of y sub n, and then here we have this, p1 of f at x sub n equals p1 of y sub n. So this proves the base case. And then in the inductive case, since we have let's think on this. So we want to use let's see here. We have we can expand f x and m as let's see, how do we do this? So we're going to expand x and m as a power series in the vicinity of x and m minus 1. Okay. Okay, so we're going to have f at x and m is a summation g equals 0 to infinity. We have f, we're going to take the j derivative. This is going to be evaluated at w n comma m minus 1 over j factorial. And this is times, keep doing w's. This is how it is in my draft, this is w's. So I keep typing w. X and m minus x and m minus 1 power j. And what we want to do is we're going to actually index this at m. So pm of f at x and m is pm of this whole summation Oh, that's not good. Let me fix that. There we go. Fix that. Okay, so okay, let's see. This is supposed to be okay, let's actually, instead of doing xn, we'll do just xn. Oh, no, sorry. Let me think on this. Hold on. So this is one of the parts I want to clean up. So let's do xn, and we're going to expand this at a power series centered at xn k, I think. And then we're going to, instead of doing PM, we're going to do pk. And this will be pk in here. And instead of m, it's k, and this is n. Actually, we can say more specifically, since z of, we have xn minus xn k is being greater than or equal to k. Wait, hold on. K is when we get the kth term. We want to do k minus 1. Yes, that's correct. Okay. Okay, so this is going to end up being this term 1j is 0. This term 1j is 1. This will reduce to that. This will go away entirely. This fraction will also collapse. The denominator is 1. Okay, and f0, this is just f. And then f1, that's just f prime. Okay, and because we have pk, we know that this difference here, this will be 0 on any projection lower than k. So this will just end up being, so first of all, this left one and then we have this right one. So this right one here, so we have this at pk and this one at P1. Okay. Make this simpler on ourselves. So let's make this one, instead of being n1, we can just do n minus 1 down there. It's gonna be too long, yep. Okay. So this term we have pk xn minus x and k minus 1. Is that what you want? Yes, it is. So this will just be pk of this expression when n is k. N is k. And that just goes away and will be this. And then we have p1 f prime xn k minus 1. Okay. Okay, f1 prime this, which is okay. This should be Okay. Okay. Okay, so what we're doing is I'm just cleaning up this earlier part. So I've made this note here to make things a little easier. So we have this function f1 of x defined as this p1 alpha. Same power series, but just p1 of alpha instead of alpha. This should be p1 alpha and the thing that we're noticing about this thing that we're remarking, is that f1 has the property that if we take p1 of f, then this is f1 of p1. So if we did p1 of f, so f is given here, if we take the p1 projection of f, we'll get the summation of p1 of alpha n p1 x power n. Since p1 is multiplicative, it just sort of follows through. Since p1 is multiplicative and linear. Okay, so I just wanted to specify that. Give me just a second. Has my audio stopped working? Hold on. My audio has stopped working for some reason. I'm not sure why that is. Well, okay. I guess I'll just ignore that for now. Okay. So we were at right, p1 of f prime, sorry, p1 of f is f1 of p1. So this just follows since p1 is linear and multiplicative. So if we just apply p1 to f, this just follows through to p1 alpha n and p1 of x power n, which is just f1 at these. Likewise, it's also going to apply for f1 prime. So if we have p1 of f prime, that's also f1 prime of p1. So we're just making a note to sort of help us out. So for each integer, so we have this inductive definition. This definition is valid since this denominator is eventually non-zero. So we have xn1 is such that it tends to 0, at which f1 prime is non-zero. So we can do this division. So we're making this note also that if we have k less than m, we project x and m onto x and k. This is just constant, so we get a convergent limit. X and m goes to xn for each fixed n. So to prove that we have f xn equals yn, we're going to prove that this z value is greater than or equal to k. So the first thing we do is we take the base case k equals 1. So we just have p1 of x, p1 of f at xn is f1 at p1. So this is the observation we had made, this one and this one. So p1 of f at xn is at p1, f1 at p1 at xn, but p1 at xn is just xn1. So this is f1 at xn1, and we had selected xn1 with this property that's equal to p1 of yn. So we have that. In order to prove the inductive case, so we've got k equals 1, so we have z of f xn minus yn is greater than or equal to k. So we have this for k equals 1. Actually, you can say circularly greater than instead of greater than or equal to. Okay, so then that's the k equals 1 case. To prove the inductive case, so we're going to prove that it's, we're going to assume that it's true for some value of k, and we're going to prove it, we're going to assume that it's true for some value k minus 1, and we're going to prove it for the value k. And we'll say this is not greater than or equal to k. This should be strictly greater than k minus 1. Same sentence, actually, but just phrased differently. We have, so if you do pk at f xn, so we split up this f xn, we split up this summation, so we do the 0 and 1 terms, so the constant term and the linear term of the power series. We separate that out from these higher terms. Since we have z of xn minus xn k minus 1, this is, actually, yeah, we can say this is greater than or equal to k. This is greater than or equal to k. This lets us simplify, so we get this pk is, we split up this term. This term has its z value as being greater than or equal to k, and then to the power of j. But j is at least 2, so it's going to have its k value greater than k, which means this whole term vanishes. This entire expression vanishes. In fact, this entire summation. So we only need the 0 and 1 terms. So we split up the 0, 1 term. So this is the 0 term. This is the 1 term, and then we just sort of do. So this one is the z value is at least k, which means when we do the Dirichlet product for the k index, we can only do this one at the index k itself. So this one ends up being at the index k, and this other one ends up being at the index 1. We could be a little more explicit about that. We could say, instead of doing this fraction, this will be right here. So this will be P1 of this first one times PK of this second one and then we split up the fraction. So by definition of our these xn terms, this is just going to end up being this whole expression. So pk of xn minus xn k minus 1 is just this whole thing, but where m is k. So we get y sub n minus f xn k minus 1, and so on. This will cancel out with this one. So this we can cancel out these fractions. So first this part, and then this part. And then once we do that, we have f xn k minus 1 and f xn k minus 1 in both these positions. So these just cancel out since pk is linear and we're subtracting. So this will go away along with this. And that's it. And that's pretty much the whole thing. I think actually this isn't even by induction. I think we don't even use an induction here. Okay, yeah, nice. Okay. So since this holds, so since we have equality where every k, then f xn is yn. Nice. Okay, so we do have, so this was sort of our first claim, was we said we're going to take this power series and we're going to say we're going to prove that for any sequence yn tending to 0, there's also a sequence xn tending to 0 with f xn equals yn. So all we now have to prove is that xn tends to 0. Now we just have to prove that. So okay, so in order to do this, we have let's see. Actually, we haven't even done any limits yet. Have we? Other than the construction of the xn series, which was a limit through k, or sorry, through m. I like that a little better. Okay, so yes, so now we just have to prove this limit. In order to prove this limit, we're going to, let's see, how do we want to prove this limit? I think what we can do, so we're probably going to do this one by induction. So we're going to say by induction, suppose, you know, xn goes to 0. Okay, so we'll say by induction, suppose x and k minus 1 goes to 0, which is true for, sorry, let's do x and k. True for k equals 1 by construction of the x and 1 sequence. Okay, then inductively, we have the limit of x n goes to infinity, x sub n k plus 1 is this limit n to infinity, sorry, we have x n k plus e sub k, this fraction, y sub n minus, this should be p sub k, y sub n minus f at x n k minus 1 divided by p1 f prime x n k minus 1. Okay, this n will go to 0. This xn will go, oh wow, what did I do here? I really messed this one up. Hold on. This should be x and k minus 1 in subscript. Okay, that's better. And this should be pk. Okay, so this x and k goes to 0. Oh wait, hold on. These should all be k's, not k minus 1s. Okay, and then x and k, this one goes to 0 by inductive premise, this goes to 0 by inductive premise, and this one goes to 0 by inductive premise, and yn also goes to 0 by premise on that. Okay. Okay, that's a little better. Okay, yes. So since we have blah blah, and then we do the limit, and we have this limit is these of these, f is 0 is 0, f prime is 0 is 1, or sorry, a unit, which is non-zero. So this will just be 0. So every natural we have x and k going to 0, and then we say since we have pk xn equal x and k, then also xn goes to 0, proving our claim. Okay, now I might want to separate this as a lemma. Because this is very long. So I'm going to take this entire theorem statement and put it down here. Just going to do that. And then I'm going to change this theorem statement to be different. So I'll say, let alpha be in a n 0, have alpha 0 equals 0, and alpha 1 in a star, then where f of x is the summation n alpha n let's see how that looks written out. Oh gosh. Let's do it this way. No, I don't want to do that. Okay. So I'm sort of reframing this as kind of a lemma. So the theorem here is we're going to say, so for any sequence of coefficients which has alpha 0 is 0 and alpha 1 is an A star, and any and the growth phi alpha is finite. So this power series has a positive radius of convergence. Then given any sequence tending to 0, there is a sequence xn which also tends to 0. So for any yn sequence tending to 0, there's an xn sequence tending to 0 with this summation, the power series summation for these xn's are equal to yn for all sufficiently large n. So the proof for that is, we'll say let f be this power series, and instead of n we'll do j, since just to keep it consistent. And then we have this, consider this function f sub 1, which is just p1 alpha. f1 is complex analytic with its derivative non-zero, and then since we have p1 yn going to 0 as complex numbers by an inverse function theorem from complex analysis, we have this sequence xn1 tending 0 with all f1 xn1 equaling p1 of yn. So we just say since this sequence of complex numbers tends to 0 and this f1 is complex analytic with a non-zero derivative, then we just apply the inverse function to these yns to get this new sequence which tends to 0. Since p1 is, and then we make this note, p1 is multiplicative and linear, so we have these compositions. And then we define these xn's as xnk's using this inductive definition. So this will be valid so long as f xn minus xn k minus 1 is defined, and so long as this p1 is non-zero of f prime. So this will be so long as these are defined, and this is fine, since as n tends to infinity, we do get as n tends to infinity, we do have these xnk's on the first projection. They're tending to 0, so they'll eventually be in the radius of convergence. And also, since the derivative is continuous and non-zero, then eventually this derivative will be, not non-zero, but non-zero on the first projection, since it's a unit. Then eventually this will also be a unit. So this f1 prime will eventually be non-zero. And then we're just saying, also, since we're just sort of summing these up with these EKs, eventually, as we sum up all these and we go through all the k, we will have a convergent limit to xn. So then the first part is we're going to prove fxn equals yn. I think we might not need to exactly do that. We can probably do this going to 0 part first. Okay, so let's do that first. So I'll say right here. So by induction, suppose that x and k goes to 0, which is true for k equals 1. Then inductively we have this definition, so this limit of these things. We do have this limit xn k, all these x and k's are going to 0. F prime goes to 0, f prime, p1, f prime 0 also converges, this all converges, and this goes to 0, since the numerator is 0, and then this front part is 0. So for every fixed k, we do have this limit. Since we have pkxn is xn k, then also xn goes to 0, proving, so this is our first claim. And then we can say So we'll continue, and by saying to prove fxn is yn, we'll consider it. So we have this first one. So this is on the first projection. So we just pull in the p1 by taking f to f1, and then we just use our premise. F1 xn1 is p1 yn. Then for k greater than 1, we expand fxn as a power series centered at xn k minus 1. And since we have this c as greater than or equal to k, we can simplify like this. So we get this splits up into this sum and this sum. This sum all vanishes since its z value is too high. Then we just expand this first summation. So this is the 0 term, this is the 1 term. These are the remainder terms, which all end up being 0. This first part, since again we have this z value being at least k, then the only way to take this pk projection is to project this one on the k index. So we get pk of this and p1 of this. Well, pk of this difference, we just use our definition. We just have this definition here. And that gets us this. And then we just simplify all these out. This term here simplifies with this term. These cancel out. And then this pk of f xn k minus 1 cancels out with this pk fn x k minus 1. And then we're just left with pk yn. So we have this equality. So we do have f xn equals yn. And that is this first proof. So this is pretty much most of it, actually. Just proving that we do have a sequence like this. And then we can, I think we can have the inverse function theorem as a corollary. Okay, so f map s to a be analytic at x0 with f prime x0 in a star. Then there is a neighborhood x0 in u subset to s, an analytic function f inverse mapping fu to u, over which f inverse f of x equals x and f inverse y is y for x in u and y in f of u respectively. Okay, so we'll just say we have since f prime x0 is in a star, then from also is continuously differentiable. I think we might need I think it's fine because it's analytic. So let me double check this theorem. So this theorem claims, I think it requires a locally convex set, but we don't actually need a locally convex set. It's enough to have it be analytic. Not this one. Oh no, yeah, yes, this theorem. Injective. So we can also say, although the reference theorem requires S to be locally convex. It is proven, let's see. Okay, so I want to use this theorem. It requires it to be locally convex, but really it doesn't matter, because we have, so this is an A star, F is analytic, then from this we find this neighborhood over which F is injective. The reference theorem requires S to be locally convex, so although the reference theorem requires S to be locally convex, we can express F as a power series centered at x0, which does converge in a locally convex set. So this is fine. And then we can say, now we can say, since F is injective on U, sorry, over U, then we have an inverse function, F inverse, mapping F of U to U. This inverse function must be, I know, right? It's just still there. Eventually, I'm gonna get to it. I think in the next section, actually, we're gonna maybe we'll use this. Maybe we'll use it. In my original draft, I made references of it in like the first section, and it just doesn't get used like at all. So I just didn't reference it. It's supposed to be a pointwise product, but it's just sort of there. It's just sort of hanging out. Okay. So this function, inverse function, must be continuous. So must be continuous since if we have y sub n, a sequence y sub n subset to f of u having y sub n go to let's just say y0 in u, then from the previous theorem we can find, actually we want to restrict this further. We want to have this neighborhood to assume f prime of u is subset to a star. Let's put this after our note. Okay, then this inverse function must be continuous, since if we have yn across n in naturals, subset to f of u having y sub n going to y0 and u. From the previous theorem we can find a sequence x sub n y0, sorry, f hold on. Okay, so this must be continuous, since if we have the sequence tending to y0, from the previous theorem we can find a sequence xn with xn going to, this should be f inverse of y0. Having f of fxn, sorry, over which the power series of f centered at I'm gonna have to change this theorem more to use lowercase f's. No, actually this is fine. Okay. Okay. Just continuous if we have blah blah blah. Power series of f centered at f inverse of y0 has, say, f at xn going to f inverse of y0. And then, since this power series is locally injective and agrees with f in a neighborhood of f inverse y0, then we must have, sorry, actually let's be a little more explicit on this. Okay, we'll say let f, is that what we want? Yeah, okay. Okay, this gives us an inverse function, so I'll write this here. Okay. And then we can say, to prove f inverse is continuous, take any, actually, we can say, take any x in U and sequence y sub n subset to the image, having y sub n going to f of x. Then let, so we'll do f, we'll say f of x. Actually, we'll do this, 0. Now let xn be f, sorry, actually not yet. Now define, okay, so we're going to define f, capital F of x. This will be a sum across n we have, okay, a sum across n of, we have f nth derivative, or sorry, these should be j's so that we don't have index intersection. Okay, so the jth derivative at the point f of y0 divided by j factorial, and this has, we're just going to have multiplied by x to the power of n, and also we're going to subtract, not here, we're going to subtract f, actually we're just going to subtract y0. Okay. Okay, so since we have, since fy0, sorry, f prime at fy0 is in a star, or we can say capital F prime at fy0 equals little f prime fy0 is an a star, and f at 0 is 0. Then from the previous theorem we find a sequence xn with xn going to, oh you're right, that should be f inverse. I don't like the way this is, the variables are turning out. Let me rewrite this. I want to use x0. No, this is fine. I'll just do something else. Over which f of y sub n minus y0, sorry, no, f of xn equals y sub n minus y0. Okay. Okay. Actually, this should be f prime at 0. This should also be f inverse. This should also be, this will be f prime at 0 is f prime at f inverse of y0, which is an a star. Okay. It follows that f, sorry. Oh yes, okay. Since f prime at 0 is in a star, then f is locally injective. So what I want to do is we're going to show, let's see, we need to show that these xn's are eventually in the f of u neighborhood. Actually, let's define this another way. I don't want to do this one. does need a little bit more work. Let's see. So because we have a sort of a weird domain, we need to find a way to guarantee okay, let's do this. Actually, okay, let's do this. Let f at x be defined as the sum n f nth derivative at x0 over, let's do j's. Jth derivative at 0 at x0 over j factorial, and then we have x minus x 0 power j so then we can say since f prime x0 is an A star, open set near x0, and agree with f when x is in S is near x0. Okay. And then we have, since f prime at x0, we'll do capital F prime at x0 is little f prime at x0, which is an A star, and f is continuously differentiable in an open set, which is locally convex. Then from this theorem we have, we'll say capital F is locally injective near x0, and then we'll say let x0 be in U subset to S, where F is injective over U. Actually, we don't want it in S. We want A, where F converges and is injective over U and agrees with F when X is in U intersect S. Okay. So we actually don't need this note. And we can say we may further restrict this neighborhood to assume f prime is subset to A star. Okay, so then we have this gives us an inverse function. Actually, since f is injective over U, then it has an inverse function f inverse, which maps f of U, actually capital F of U, to U. And then we can say notice that we have an inverse function for f over U intersection with S by restricting f inverse to S. If we have f inverse as analytic, this will prove the theorem. Okay, so to prove f inverse is continuous, take any y0 in this image, capital F of U, and sequence yn in capital FU having y intended y0. Then from the previous theorem, we can find a sequence xn in A star with xn going to f capital F inverse y0, over which f xn equals yn for sufficiently large n. Notice that this means, this implies that y sub n is in f of U. Actually, let's do it this way. Since U is an open set, then eventually, then for sufficiently large n, eventually x sub n is in U, and actually we'll do a sequence. No, this is fine actually. Sufficiently large n, eventually xn is in U, so that y sub n is in f of U, so f of U is an open set. So this proves that f of U is an open set. Then we can say So this is also an open set. Moreover, since f is bijective from U to, or rather just injective over U, then and x of n equals, f of xn equals y sub n, then also f inverse y sub n equals x sub n, which tends to f inverse y0. Okay, so we're going to consider this capital F function, this power series. F converges in an open set near x0 and agrees with f when x is also in S is near x0. Since f prime x0 is little f prime x0 is a unit, and f is continuously differentiable in an open set, which is locally convex, then from this theorem, back from differentiability or integration, f is locally injective. So we may find a neighborhood U over which capital F converges, is injective, and agrees with f when x is also in S. We may further restrict this neighborhood to assume f prime of U is subset to A star, since this is just a neighborhood of x0, which has f prime x0 is in A star. Okay, so since f is injective over U, has a bijective inverse function, so f inverse, mapping the image back to U. We do have an inverse function for little f over the intersection U intersect S by restricting f inverse to S. So if we have f inverse as analytic, this will prove the theorem. So we just want an inverse function, an analytic inverse function for the function f over some neighborhood. So all we have to do is prove that our capital F inverse is analytic. So first we're going to prove it's continuous. So we'll take any y0 in this image and sequence y sub n tending to a point y0, which is also in the image. And then we'll take, actually this sequence doesn't need to be an FU. It should be any sequence in A tending to y0. The previous theorem gives us a sequence, so xn, this shouldn't be an A star. Xn subset to A with xn tending to f inverse of y0 over which f of xn is yn. So for sufficiently large n. Since U is an open set, eventually xn is in U. Actually, we can say yeah. Where was I? Over which fn is, yes. Since U is an open set and xn tends to this point f inverse of y0, which is in U, an open set, then eventually xn is in U, so that eventually yn is in f of U, the image fu. So f of U is also an open set. Since we have f is injective over U, and f xn is yn, then f inverse yn is xn, which tends to f inverse y0, and this proves that f inverse is continuous. Nice. Okay, so it's continuous. Okay. Nice. Okay, so f inverse is continuous. Now we can prove that it is differentiable. So we have, okay, so to prove that f inverse is indifferentiable, so to prove that f inverse is analytic, it is enough to prove that it is differentiable since an open set so it's enough to prove that it's differentiable since an open set constitutes a proper domain and differentiability in an open set, in a proper domain implies analyticity. Okay, so we just need to prove that it's differentiable. Let me also double check that theorem to make sure we didn't weaken it somehow. Should be fine. Differentiable over proper domain. F is analytic. Okay. Yeah, that's fine. Okay, so where were we? Right down here. Okay, so take any sequence. We'll have x sub n, or rather, yeah, we'll just do y sub n. Subset to f of u, having y sub n go to 0, or sorry, y0. Actually, let's do it this way. No, yeah, this is fine. Take any y0 in f of u and sequence yn having yn go to, y0. Then as above, we have f of y sub n equal x sub n, which goes to f inverse of xn. Okay. So we can calculate the derivative f prime at f inverse of y0 as follows. Limit n goes to infinity of f at xn minus f at f inverse y0 over xn minus, I really don't like that I have to do this. Okay. So we're going to use y0 just like before, and the sequence tending to y0. As above, we have f of yn equals xn tending to f inverse of xn. So we can calculate the derivative f prime at f inverse y0 as follows. So we get this limit. This fraction didn't go correctly. Actually, we can say, instead of subset to f of u, should be subset to f of u without y0. Okay, yes. So in order to calculate f prime at this f inverse y0, we just use this limit. So we have f at xn minus f at f inverse y0 divided by xn minus f inverse at y0. And then we note, so actually we can do a change of variables right away. F at f inverse y0 just becomes y0, and f at xn is, well, xn is f inverse of yn, so this just ends up as yn, when again f xn is f inverse at yn. Okay, and then since f prime of u, actually we can just say f prime at f inverse y0. Since f prime f inverse y0 is in A star, which is an open set, then for sufficiently large n, the above difference quotients will also be in A star. From continuity of reciprocal, we have the derivative. And then we just swap around the numerator and denominator. I'm not sure how I should format this, with the prime and the f inverse. Instead of using capital F inverse, I might just use capital G. That might be a little better. Let's do that. I'm going to do that. Okay, I think that's it. I can also, instead of writing this as a corollary to this, I can do a corollary to this which has these not being 0. Yeah, and f inverse prime x. Yeah, that would be an option. Okay, let me see. I want to try to rephrase. Maybe I can rephrase this theorem. Actually, no. I want to leave this as this. I'm going to add a corollary to this theorem. Instead of having this as a corollary, this will be its own theorem. But I will have a corollary here. And we'll just say actually no. I'll do this instead. This should be alpha 0. Okay. This is fine. Okay. Okay, so I think this is good. So we have this power series. F converges an open set near x0 and agrees with F when x is an S and near x0. Since F prime is an A star, F is continuously differentiable in an open set, which is locally convex. So we have F is locally injective. From this we may find a neighborhood x0 and U subset A over which F converges and is injective and agrees with F over this intersection U intersect S. We may further restrict this neighborhood to assume F prime of U is subset to A star. Since F is injective over U, then it has a bijective inverse function, G mapping F of U to U, notice that we have an inverse function for f over the intersection u intersect s by restricting g to s. If we have g as analytic, this will prove the theorem. To prove g is continuous, take any y0 and f of u, take the sequence converging to y0. We consider this power series of f centered at g y0. Previous theorem gives a sequence xn and natural subsets to a with xn tending to g of y0, over which f of xn equals yn. Okay, this should be g of y0, which is in u. This is probably fine. Okay, since u is an open set, eventually xn is in u, so that eventually yn is in fu, so that f of u is also an open set. Moreover, since f is injective, then also g of yn equals xn, which tends to g of y0, proving that g is continuous. Since an open set constitutes a proper domain, proving g is differentiable is enough to prove that it is analytic. So take any y0 in f of u and this sequence, which is different from y0 but tends to y0. And as above, we do have f of yn equals xn, which goes to g xn, and by injectivity also xn is not g of y0 ever. This lets us calculate the derivative, f prime at g of y0 as follows. So this is this. Since this derivative is an a star, which is an open set, for sufficiently large n, the difference quotients will also be an a star. So continuity of reciprocal then gives the conclusion, so we just reciprocate this, and we get this. But this is just the definition for g prime of y0. And that's it. So our inverse function is differentiable in an open set, which makes it analytic. And then if we just take a g and restrict it to this intersection, u intersect s, then it's the inverse function for f over this domain. If we take the image of this domain, it's just the inverse function for this little f. And that is analytic, since if we just restrict the domain, it'll still be analytic. And that's it, we're done. So that's inverse function theorem. Kind of. Well, yeah, pretty much. There's one other note that maybe we want to do, which is, so for this theorem, we've essentially proved that if we have a general power series, that it's an open mapping, meaning it takes on every value in a neighborhood of its image. So that if we have a power series taking on some value, like for example a0, alpha 0, takes on that value, then it actually takes on all the values in a neighborhood of alpha 0 in an open set, which is quite significant. That's quite a lot, because the open sets for our space A are quite large. So that's pretty nice. This is also interesting because our our inverse function theorem applies for any domain. In particular, we just proved it for the open sets domain. The inverse function is also an open set. The inverse function is also analytic. It's actually just given by a power series. Theoretically, since a power series converges dependent only on the first projection of its input, the composition of the two power series will also converge in a vertical set dependent only on the first projection of the input, and will just be x. So in addition to the fact that we get a neighborhood where the inverse function applies, that neighborhood is actually quite large in a certain sense. In that it really only depends on, for the most sort of nice analytic functions, like these analytic functions that converge in a vertical set, in a cylinder set, I mean, we get a really nice, that the composition also converges to the identity function in a cylinder set. It's very nice. So that's that. I think that's the last theorem we have for this section. Yes, it is. There's some other theorems. We could do an example. One other sort of example. So, it should hopefully be evident that if our function does not have its derivative as a unit, then it cannot have an analytic inverse function. In fact, it can't even have a differentiable inverse function. And the reason that it cannot have a differentiable inverse function is that if it did, then it would have to satisfy this identity, that if we take the derivative of the inverse function, it's just the derivative of the ordinary function at the inverse value, but just reciprocated. If the derivative isn't a unit, there's no possible way that this could work, since you can't take the reciprocal of a non-unit, something that is not in our set A star, the set of units. There's no way to do that. So it is true that if the derivative is not a unit, there won't be a differentiable inverse function, let alone an analytic inverse function. But we can actually prove something a little stronger, which might be a little interesting. We can actually disprove this theorem if the derivative is not a unit. So not only would this theorem fail if the derivative isn't a unit, this one will also fail if the derivative is not a unit. And we can prove that. So we can prove specifically, we can prove that if we have a power series with its derivative being a non-unit, even if the radius of convergence is finite, or sorry, is non-zero, even if the radius of convergence is non-zero, then in fact there will still be sequences y sub n tending to alpha 0 over which no such sequence xn exists. So there is, in particular, actually, even stronger. We can show that there's a sequence in approaching alpha 0. So it's in the domain of the power series, approaching alpha 0, but such that there is not any sequence which even agrees with yn. So these yns will not even be in the image of the power series eventually. We can actually prove that, which is interesting. It's not what you would expect, I think. In fact, it's going by the intuition that one might get from complex analysis. It's actually sort of the opposite of what you would think. In complex analysis, it's true that every power series is an open mapping, even if its derivative is non-zero, if its derivative is not a unit. But this is not actually true in this case. That sometimes if the derivative is not a unit, in fact every time that the derivative is not a unit, it will have this property. So let me find my counterexample, and then this will be the last thing we do today. Hopefully, I think this should be fast. This does not look fast. Let's see. Okay, so this proves both that functions which are analytic in an open set and have this proves that inverse function theorem applies for analytic functions so long as their analytic functions so long as their derivative is a unit. Naturally, since actually we can say naturally, since any inverse function has its derivative, any differentiable inverse function has its derivative as the reciprocal of the derivative of its inverse, then logic functions, so then it is also necessary for the derivative to be a unit for IFT to apply. In the case that our function is analytic in an open set, our earlier theorem also proves that analytic functions with derivatives being a unit, actually we can just say this also proves that such functions are open mappings. Analytic functions are open mappings near points for which, analytic functions defined over an open set. Yes, so the earlier theorem also proves that analytic functions are analytic functions which are defined over an open set are open mappings near points for which their derivative is a unit. This is not true. Rather, open mapping fails in the case that the derivative is not a unit. However, okay, so the theorem is let F map S to A be analytic and F prime at x0 in a set minus A star. Then there is a sequence y sub n going to y sub n in natural having y sub n going to x0 but and a neighborhood. neighborhood U subset to S over which f of I think this is done in two parts actually, so this might take a little bit. So actually, in fact, I think we will maybe not do this today. I will finish writing the theorem statement though. Actually, we can just say this. There's a neighborhood x0 in U subset to S for which f of U is not an open set. That'll be a little simpler. Before we close out here, okay. Yes, so that is all for today. Today was very fun. We finally got through this theorem that we've been sort of looking at for a while. That if we have a function, this one, if we have an analytic function with a unit derivative, then there's a neighborhood and another analytic function, f inverse, over which f inverse is the inverse function, and it also is analytic. So inverse function theorem, if we have an analytic function with a unit derivative, then it has a neighborhood, it's locally invertible, it has a local inverse function. Yes, so that was fun. Next time we come back, we'll investigate this sort of counterexample to open mapping. But for now, that will be all. Thank you so much for joining me again. I hope you learned a lot. As always, if you have any questions, ask them now. Although, of course, you can always ask questions at any time during the stream. But if you have any questions, ask them now. This is your last chance for today. Fun as always. I agree. I very much do have fun. It's really exciting. Yes, it's very fun. Okay, well, if that's all, I will. Oh, that's okay. Well, the stream is always recorded in case you want to go back and look at it again. And of course, the the whole LaTeX file is available to you on the Discord, so you can look at it whenever you want. But yes, so thank you for coming and watching and hanging out, and I will see you next time. Goodbye.